So Ed Overton is a professor emeritus in the Department of Environmental Sciences, School of Coast and the Environment at LSU. His research interests include understanding the fates and distributions of hydrocarbons following an oil spill, the environmental chemistry of hazardous chemicals, and the detection of environmental pollutants at the site of sample collection. He has been active in understanding the fate and effects of petroleum hydrocarbons in marine environments from oil spills since the 1978 well blowout at the U.S. Doe Strategic Petroleum Reserve West Hackberry site. Wow. Did I say that right? Was it close? He's given hundreds of live interviews concerning the Deepwater Horizon oil spill to international print, radio, and TV media sources, including an appearance on The Late Show with David Letterman, as well as all major U.S. TV network and cable news shows. I'm surprised that wasn't your fun fact. And he has also been an invited speaker at dozens of national and international scientific meetings and seminars on topics associated with the oil spill. So his fun facts is that he enjoys boating and in particular sailing. So without Overton, go right ahead.
Thank you, Monica.
Sure.
Let me, before I start talking about this, let me make a couple of comments. First of all, the Deepwater Horizon oil spill was just a horrible event, but it provided an opportunity through a number of resources to learn a lot more about what happens during oil spills. First of all, BP put up a heck of a lot of money, the Gomery project. Now, the Gomery project started in about 2011 or 12, and it's nearing the end of its life. So we're starting to synthesize what we've learned in the first 6 or 8 years. The other big impact was, of course, the natural resources damage assessment, which Lisa handled and did such a great job on. And that involved a collection of massive amount of sampling and data during the first couple of years of the spill. Now, since the case has now been settled, a lot of that information, all of the data that was publicly available, is getting turned into papers and information. So we're right now, after 6 or 7 years after the spill, just starting to synthesize what we really know and don't know. So in the next 2 or 3 years, it's going to be really exciting to actually get down and see what we know and don't know, what we should do and shouldn't do the next time around. So there are lots of information, and I certainly, what I'm going to present today, I want to do what Jerry Galt says: we reserve the right to get smarter later. So, and I hope in the next couple of years we're going to get a lot smarter, because now, you know, that when you're in the middle of an event, it's hard to know the long-term outcomes. But we're well beyond the middle of the event, and we're now starting to get some idea of the good science. So let me just go through a couple of ideas here. I grew up learning environmental chemistry with the concept of the chlorinated pesticides were the pollutant. You had heavy metals and organics, and everybody knew that DDT was the poster child. And what I want to point out is that oil is a lot different from DDT, and our concept of it as a pollutant ought to reflect the chemistry of oil, right? So what is oil? And I say this because in the spill, I can't tell you how many times people treated oil spills like you would treat a DDT spill, right? So quickly, I'm going to try to explain the difference between DDT and an oil spill. First of all, where did the oil come from? It came out of the atmosphere, came out of thin air, right? Through photosynthesis, and we ended up, this is the carbon cycle, and we ended up producing biomass. Now that's, this little signal, all of us are made out of that. All the bacteria, all of the living organisms, if you squeeze all the carbon and hydrogen and oxygen, you get approximately this formula. And of course we produce all the oxygen we breathe. Now, this biomass dies, whether it's bacteria or the dinosaurs. You know, in the ocean, of course, it's bacteria and plankton. It dies, it sinks down. This reaction to a chemist is called a reduction reaction. We're taking energy from outside, energy from the sun, kicking out the oxygens and replacing it with hydrogen, right? Chemically, that's a reduction. The definition of a reduction reaction is replace oxygen with more electronegative, replace hydrogen with a more electronegative element. That's oxidation, this is the reverse. This stuff goes down to the bottom and under temperature and pressure gets further reduced, right? So basically you knock that oxygen off, and hydrocarbons generally don't have a lot of oxygen in their molecular structure. I know you're excited. In the next slide, we're going to show you some of those molecular structures. So this is where the energy is stored, right? So the energy is stored in this, and of course we bring it up. And why do we bring it up? For their energy, right? We turn it, oil is almost all used for fuels. So when we drive around, fly around, boat around, we're using that. Now, when these reduced hydrocarbons come to the surface, we can burn them, as we do in cars after it goes through the refining process, or there are naturally occurring microorganisms that convert this reduced form back into biomass. And the biomass is, of course, another way of saying more bacteria, right? So as oil is degraded, we can get that energy from burning it, or you can get that energy for life. So we go through a reduction reaction to produce biomass. It gets further reduced, and then we use it in the oxidation. It goes back, and notice the products here are CO2, right? So that's what oil is, and it naturally goes through this cycle. Now, I'm going to spend the next half an hour describing this, and I'll expect everybody to take notes. But suffice it to say that this is what oil is made of. And there's some truisms about oil. First of all, oil contains thousands, maybe hundreds of thousands of individual compounds. So it is a really, really complex mixture of chemicals. But what we do know is that virtually all oils, regardless of where they came from, contain these same structures. So if there's an oil spill off the North Slope of Alaska, or in the Santa Barbara, or in the Gulf of Mexico, or off the East Coast, we know what's in oil spills. How many times did you hear people standing up in front of the media and said, "We don't know what's in that oil"? Bull, we know what's in oil. Oil is a natural product. It's coming out of the ground, and we know very accurately. What we also know is that oil from different sources contain different quantities of specific chemicals. So if it's a light oil, it contains more of the small molecular weight structures than a heavy oil. A heavy oil contains more of the high molecular weight structures, which are more viscous and have less vapor pressure. But all oil is more or less the same, with the exception of that. Now, from this area, sorry about that, from this zone down, we're looking at really large molecular weight compounds that are essentially insoluble. We're looking at asphalt. We're looking at what's in the residue that we can't turn into a useful product. Oil goes into a refinery, you turn most of the components into something you can turn around and sell, and when you've got all that good stuff out, you got some gunk left over, you heat that gunk up, you add some sand and some gravel, then you put it on the road, you got asphalt, right? Now, I'm getting ahead of myself. These are the components that you heard Tim talking about, the water-soluble components and the volatile components. These are the type compounds that give oil its greatest value in terms of a product, but also cause the environmental issues. These compounds are virtually insoluble. They're the residues now. And we know that in oil contains mostly this stuff up here. These are the toxic components in oil. These are the other components in oil. And let me get back. So not all of the compounds in oil we have to worry about as being toxic. What we are worried about are those compounds that can have a route of exposure, because you can have an extremely toxic chemical. I got a mouthful of toxic chemical called gold in mercury. But there's no route of exposure because it's insoluble in my mouth, right? But that's not the case with these compounds. These are fairly water soluble, they dissolve, they evaporate, there's your routes of exposure. This stuff is insoluble, and you can chew it and it's not going anywhere. If you ate it, it would end up passing through the system, if you know what I mean, right? So what we are worried about are those dangerous chemicals. Now, this just adds to this oxidation reduction. Oil is the reduced form of carbon, and it gets converted by natural processes, most of the time fairly quickly, into carbon dioxide. If it blobs together or it gets below the surface, Gene talked about the anoxic zone, it's not going to be a fast reaction. this reaction is very, very slow, so it does not change very much. So if you want to make oil spills go away, you keep it up in this zone of the environment. Don't let it get down in here. Keep it out of the anaerobic zone, keep it oxidized, and let Mother Nature handle her effort. What about compounds that do get exposed? This is an example of animals. Some animals have natural enzyme systems that can oxidize oil in the body. That means that they are recognizing a pollutant and trying to make it more water soluble and excrete it. Some don't have it, and some do have it. So those of us that do have it, and that includes you and I, and all the finfish and the shrimps and the crab, they have an uptake, and there's a fairly rapid deposition. There's no bioaccumulation. They have an uptake, so you don't get bioaccumulation. Other organisms, like orchids and plants, uptake slow deprivation, so you can get bioaccumulation, and then if that organism is eaten, biomagnification up this food chain, right? What happens during this uptake of deprivation? That can cause a problem for that organism, right? So that makes them sick. What happens to a sick organism? A sick fish? You know, I'm a new granddad, and I joke around and I say, what do you call a granddad fish? Reckless, right? They simply can't swim fast enough. They've lost their energy, and so the natural scheme of things is that damaged animals, be it by age or by oil spills, are going to be cleaned through the system. So this poor sick, I don't mean to imply that it didn't hurt that animal, but that animal didn't cause ecosystem problems. It got cleaned out of the system. If that animal had not been exposed to oil, what would have happened? It would have grown old, just like Granddad Overton or Granddad McDonald, and been eaten out of the system. Now, thank God there's modern medicine, and that keeps us granddads going. But when you get to be my age, there's always something that ain't quite right, right? So this is another point about oil spills. The oil undergoes a lot of weathering, right? This is a complicated picture, but it's not really too bad. Oil in this environment here, it gets evaporated and dissolved quickly, turns to oil residues. That oil residues moves through the environment. It undergoes compositional changes. The chemical oil are lost, either lost by evaporation, degradation, or oxidation, either bio or photooxidation. The quantities get less and less, and what we do know is that weathering changes the original composition of the oil. So these dudes over here are your most dangerous form because you've got these volatile solubles. Once you get over to here, you're looking about components in oil that were in that bottom half. Remember I talked about the insolubles, right? Now that came from oil, but it's not nearly the same toxicity or environmental damage as you've got up here, right? So as oil goes through the environment, it goes through those changes, and then we get to this slide about when all of the dust settles, how does oil cause environmental impacts? What are they? And of course, the big three are toxicity and route of exposure. You can't just look at toxicity. You can't look at the gold in my mouth or the mercury. You got to look at its route of exposure, right? Really, really important. Tim talked about it. Gene talked about it. Route of the toxicity and route of exposure in those large molecular weight structures simply don't have a route of exposure in most cases. There's always a case where a turtle is snapping at a little particle like that and some fiddler crab's digest it. In most cases, those compounds pass through the system. Always an exception to the rule. Don't quote Overton and saying these things don't cause problems, but in general they don't, right? Now, so this is the biggie, and this is the one that worries you most, but oil also coats and smothers, whether it's coating leaves here and disruption the function of the plant leaves, or coating this animal and causing it to lose its thermal digestion. A bird like this can't ingest the oil in preening, but smaller birds certainly will clean themselves. And what is that cleaning? Route of exposure, right? So you got to keep your eye on the ball, the route of exposure, not just the toxicity. A fairly small percentage of oil, 4% or so of fresh oil, contains the toxic compounds, the aromatics, the BTEX, the PAHs, and things like that, right? But all of the components in oil are part of the covering and coating, and almost all of the oils are degradable by natural organisms. And if you go into an environment like a coastal marsh where the oxygen levels are pretty low and it's the summertime and it's hot, and you add more biological oxygen demand, you're going to lower the amount of oxygen available for normal living in that marsh down below where the normal residents, and that's another source of impact. So these are your big three if you want to find out what can oil do to my ecosystem, be it in the marsh, be it in the deep water, or wherever. Now, there are a couple of other issues. Certainly, when you have oil degrading, you're producing a lot more bacteria that weren't normally there, right? So you've got this idea of carbon enrichment via the bacteria plankton. And sadly, of course, this is where the SSCs come in. Some remedial activities can cause more damage than good. For example, it's not a good idea to leave these heavy soaked booms, these absorption booms up here. It's heavy, it's rolling across the marsh, right? Where don't we want the oil to go? If oil is coating this marsh, as it is, right, we want to keep it on the surface. Don't push it under the surface. What happens when it goes under the surface? No oxygen, and it stays there until it gets disrupted again. So part of the whole idea of responding to spills and understanding the science of it is to understand what is oil made of. Now, if this were a DDT spill, I'd be giving a different talk. DDT spills don't get oxidized easily. They are already oxidized. We have replaced, in DDT, we replaced carbon with a hydrogen. On carbon, we replaced the hydrogen with a element more electronegative than hydrogen. Oxygen, natural process, chlorine, fluorine. The chlorofluorocarbons. What did we know about the chlorofluorocarbons? They went in the atmosphere. What happened when they got in the atmosphere? Nothing. They didn't go away. There were no natural mechanisms. So they ultimately floated up to the upper atmosphere, the stratosphere, and now we've got a whole different set of chemistries going on in the stratosphere. But in the troposphere where we live, chlorocarbons, DDT, don't go away very fast. So you have to think about them as a different kind of pollutant. Oil spills, we know they react. We want to make them react. One way to make them react is take a glob of oil and break it into really small particles, right? A glob of oil can't degrade very fast because most of it is covered, this molecule of oil is covered by a bunch of other molecules of oil. So we break it into little pieces, little parts. How do we do that? Well, we allow Mother Nature to wash her hands. We spray a soap on it. We call that soap detergent, right? So if you do it, as Tim pointed out, in the right spot, where you're not doing it near shore where you've got this dilution, you are helping Mother Nature do her job. So this is part of understanding the chemistry of oil spills. Let's see, going the wrong way. A couple of other issues here is that we need to understand about the processes where we get information. So how much is in oil? There are a number of processes where you go from a collection of sample, you extract that sample, you run it through instruments, and you get data. The data that Gene showed in his was all done in our lab in collaboration with Gene in understanding how much is in oil. What we found out was that it's not just the ecosystem that we need to worry about. We need to worry about the folks that are involved, right? And there's two classes of people in addition to all the critters. And when I say critters, I'm talking about bacteria on up, right? Bacteria to whales, right? But what about the people? Well, you've got the responders who are actually working out here. And this stuff is, the vapors are coming up, and it is just literally intolerable. These people were working, and they were having to wear respirators 24 hours a day. They're not going to work and come home and watch TV at night. They're living out there. So it's a big deal. So exposure of toxic chemicals in oil, and there are, which ones are they? What are the toxic chemicals in oil? Small molecules, volatile molecules, light molecules, things that dissolve and or readily evaporate. So you get exposures. There was some issues. People were worried about recreation exposure in beaches. There was disruption of normal job functions, and certainly a great deal of uncertainty. What do you do when you get nervous? What do? I drink. Not a good idea. I'm not a smoker, but some people smoke, right? And some people smoke things they shouldn't be smoking. other than cigarettes, if you know what I mean. Right? But that's a health hazard, right? They are not getting exposed to the toxic chemicals in oil, but they're getting exposed to the consequences of an oil spill. And that happened a lot in South Louisiana. There's a potential consumption of seafood. I don't think that was a significant issue in the Deepwater Horizon. Between the various agents at EPA, FDA, in states, they analyzed tens of thousands of samples and basically found no levels of concern in commercial harvest. I went out, my son went out and caught some fish, some good speckled trout. Now it wasn't in a closed zone, of course. It was in an open zone up in the marsh, but boy, it was good eating. He said, I got only 3, I got 30 minutes when we're talking. Oh my God. All right, the health effects associated with anxiety, I already talked about that. And of course, there are health effects associated with economic loss. Macy's makes their money at the Thanksgiving Day parade. Maybe that's where they're advertising. Gulf Coast makes their money in the summer. They got people going to those, they own a nice condo down there, and you rent it out in the summer. And to help pay the mortgage in that condo. Well, if nobody's renting that condo, you're eating that. And so, some of those condos are pretty pricey. So this is again what happens to weathered oil. I'm going to run through this. What Tim talked about this, and I'm going to end up, when you have the effects of weathering, the longer oil weathers, the less you can do in terms of a response. So in the big three he talked about, in the big three in 1970 is the big three in 2010, right? How many people sleep on a different bed than you did 20 years ago or 40 years ago or 70 years ago in my case? We all sleep on the same bloody bed. Might be bigger, rounder, got a better company. But people were saying, well, we're still using the same techniques that we used in the Ixtoc. Yeah, that's right, because they work. These are the options, and the longer you wait, the less effective those options are going to be. That's part of the science. You got to make a decision, and there's a window of opportunity where these things work, and we want to take that window and make it work very quickly, right? So what Tim pointed out, and I wanted to concur in this, is that use of dispersants, it's really in a big oil spill, in a massive oil spill, you have a route of encounter. A boat carrying some sort of a boom behind it is only going to encounter a fairly narrow swath of oil. So if you don't use large planes to get out there and try to break that oil up, you're not going to encounter much oil. So you can collect a little bit of oil, but you're missing the whole point. We don't know how much dispersants kept oil from coming ashore. Let me say that. We don't know how much oil didn't come ashore without dispersants. But we do know that oil that got dispersed didn't come ashore, right? Think about what dispersant is. You got a glob of oil that's sticking together. You break it into small particles. Those small particles get carried by physical motion down into the water column and start diluting. Has anybody ever seen anything that's diluted get more concentrated? That is absolutely against Mother Nature. Once it gets diluted, it ain't coming back, right? So dispersed oil didn't come ashore. It's a possibility that a little bit of one droplet of oil that had a dispersant in it made it on shore. Yes, that's not dispersed oil. Once we disperse oil, we are protecting our coastal environments. Use of dispersants is a decision. We are causing potentially more damage in the deep water relative to what we could occur. It's one of these, I got a bad decision here, you're in a wreck, right? What are you going to do? You're going to put a tourniquet around the arm or let the guy bleed to death, right? So neither one of them, putting a tourniquet around the blood supply of your legs, not a great idea, because the toes need blood too, right? But you got to do something. In my opinion, we need access to all of these capabilities. And I guess my 1 minute is up.
We got
Okay.
One more.
Oh, I probably said enough. I probably said too much already. Let's just end it with that. Now, we will all be happy to answer questions. Thank you.